Today we're going to be continuing with 2D kinematics. We'll do some example problems later. First we're going to talk about some tips for solving 2D kinematics problems. So we already have our kind of steps that we use for solving kinematics problems in general, draw, sketch, identify variables, etc. These are more specifically for these 2D problems where we have motion in the x direction and motion in the y direction. So in many of these problems we have an object that is like thrown through the air or falling through the air. These are generally classified as projectile problems. So in those sorts of problems, which are most of our 2D problems, we have our y acceleration is equal to minus 9.8 meters per second squared, and our x acceleration is equal to 0. And this is true almost always for projectile motion. Some of our 2D problems aren't like that. Some of our 2D problems are like we have we're looking at the football field from the top down and we have someone walking across the field and this direction is the x direction, this direction is the y direction, where we're not looking at things like flying through the air. So gravity is not affecting their motion in the way it does for, these sorts of things. The specific value for the y acceleration, this is true on Earth's surface, but I could imagine giving you a problem that happened on the moon or something. And if I did that, I would say, a guy throws a ball on the moon, parentheses, g equals 1 point whatever meters per second squared. I would give you a different value if that was not what you're supposed to use. Okay. All right. The fact that the x acceleration is 0, this is important. This means that Vx is constant, and that is often very helpful in solving problems because there's no acceleration. Yeah. Okay. The next tip. So this is like tip number 1. The next tip is that very often our procedure in these 2D problems is to use one of the two directions, x or y, to find a useful variable. Usually that's the time. And then use that in the other direction to solve for whatever we're finally looking for. So we'll call that the intermediate variable, which is usually time, and then plug that into the other direction. This isn't strictly true. There are some 2D problems where we only need the y direction information to solve it, or we only need the x information to solve it, but generally we have to use one to solve for what's going on in the other. Okay, I'm going to erase this to make room. We have one more tip, I guess. And before I talk about this, we're gonna get to this tip by analyzing a little bit of motion here. So let's imagine that I have a person who throws a ball at an angle with some velocity, right? We know in our everyday experience what path this is going to take, right? This is going to follow a arcing path, kind of like, I want to make sure this is in the frame, like that. I don't know if you could see that, but so it's going to follow, some path that generally looks kind of like that. Now, at different points along this path, our ball is moving in different directions, right? And what I mean by that is here, our ball is moving up and to the right. Here, our ball is not moving up and to the right. Our ball is moving down and to the right, which means our velocity has changed, right? Our velocity is a vector, so the direction it's pointing matters. So if it's pointing up over here and pointing down over here, those are different vectors, so they're different velocities. Okay, so the point is, at each point along this arc, our velocity is actually tangent to the arc. And there is a particular point right here where our velocity is horizontal. That is, it only has an x component guess I'll say Vy. Vy is equal to 0. So in general, this is true for 2D motion, but I guess to sum this up in a sentence, at the highest point of an object's motion, Vy equals 0. So my simple explanation of why this is if Vy did not equal 0 at the highest point, it wouldn't be the highest point, right? It's still moving up, and so a little bit later is going to be a little bit higher. Okay, while we have this diagram up here, it is kind of useful to think about these velocity vectors and their components as I've drawn them. So here we have an x component and a y component, right? An x component and a y component, and an x component only, an x component and a y component, and an x component and a y component. Okay, so what I want, and this drawing isn't perfect, but what I want you guys to kind of see, at least, or believe, even if the picture doesn't show it perfectly, is what I said before. Vx is a constant because ax equals 0. Right, so this component of all of these is staying the same. Yeah, I drew this one a little longer, but in general, the other ones are pretty much the same. Our y components are changing a lot. So here our y component, our y velocity is pretty big and up. Here it's up and a little smaller. Here it's 0. Here it's down and small. Here it's down and a little bit bigger. So with what's going on in the problem, we should have some idea of what to expect for the velocity components, depending on if an object is going up or down. We can kind of draw a picture like this for any of these problems. Okay, the last tip, I guess, if you want to call it a tip, is for some problems in the 2D kinematics family, we will need to use the quadratic equation. This is not true for every 2D kinematics problem, certainly, and I am not going to give you one on a test that requires you to do the quadratic equation. The reason is it's just a place where people make a lot of math mistakes, and it's no fun. So if you're on a test and you run into a problem that you think you need the quadratic for, you are either going about it the wrong way or misinterpreting something, because I will not give you a test problem that requires you to do that. Homework problems. Yes, homework problems are fair game, so you probably will need to use the quadratic equation for a homework problem or two. Okay, this concludes our 2D kinematics tips. So next we're going to do some examples of problems.